Start.
It's half of the class.
Hello and welcome back to Calculus 3, section 11.7, Motion in Space. We already talked about vector-valued function r being a path. So now we know that we are supposed to differentiate once for velocity, twice for acceleration. If you have acceleration vector, you can integrate once for velocity and one more time to get the position. So the speed, we already had the example in the last section. The speed is going to be the magnitude of velocity. So all of those concepts from the example from the previous section are still there. Path is going to be defined by r of t. Velocity is going to be v of t, which is the derivative of r. Speed is going to be the magnitude of, let's put just velocity. And acceleration is vector a, vector a of t, which is the second derivative of position function or the first derivative of the velocity. There is one more concept that it's generally not, well, it's almost never included in the calculus books. It's jerk. That's the change of acceleration. You experience jerk every time when you slam on your brakes or your gas pedal, right? When you push gas pedal too quickly, right? You experience jerk because you hit the seat, right? And if you slam on the brakes, which is also acceleration, just deceleration, so rapid change of velocity. So if you have your gas pedal is accelerator, your brake is decelerator, and they both change velocity. So that's your second derivative actually. And your foot on those pedals actually controls the jerk, because if you are pressing too hard, you are experiencing those forces, and if you are pressing it slowly and lightly, obviously you are not. So we can add that if you want. We are not going to use it anywhere, but we might want to add to the collection of these things just for the sake of physics and understanding the world around you.
So it's the rapid change of velocity?
No, it's just change in acceleration because it's derivative, right? It would be dA dt, so you're changing acceleration. But see, you always have, jerk is always there. It's just that you might experience it or you're not. For instance, we feel earthquake when it's above whatever 2 on the Richter scale, I believe. But the planet surface of the planet, it's constantly shaking because the core is rotating and stuff. We just evolved to the point where we don't feel it, right? As a species that's been on the planet for 100,000 years, right? We don't feel that constant tremor that it's on the surface of the planet, and in the same sense, right? You are not experiencing jerk when you are slowly pressing the pedals, right? Lightly pressing the pedals. But as soon as you push it a little bit harder, you will either be kissing the steering wheel or you will be hitting in the back, which is the reason why you have the right. Anyway, so the path will be, we had the example already, right? The path is the, let's say, helix. The particle takes the path of the helix, and then you can calculate the velocity, speed, and acceleration as we did the last time. Now we can quickly work out the example over here. So let's say that your R is given as t, t squared, and t cubed. So compute all of the concepts that we talked about. So you have velocity, you have the speed, and you also have the acceleration. You can calculate jerk also if you want to. No, it's just well, you can put, I don't know actually, because well, we use R in Calc 3 in physics. Is no, that's the units. Units. S, but then in mathematics we usually use S for the path, S of t, in math. So it gets confusing in a math class.
I think for speed you just like the
S. Of V, yeah, that's what we're going to use.
Why don't you use R of t for that? Should it be S of t?
Yeah, it could be anything, but we are just calling it R because it's a radius, because you can, it kind of swipe, because you start at the origin and you're always, it stretches, so it's kind of radius-y concept. Yeah.
Radius-y?
I know it's not a word.
What is the definition of radius-y? You're not thinking about it so hard. See, your phone can't do it. Do that, can you? What do you have on?
Don't poke into it. You're not gonna like it.
Like Jill or something? What's the name of the AI?
I have two, and I don't use any of them. No, two different AIs in Samsung phones now. No.
Well, no, I thought he was trying to get phone AI.
And then the Google one. Exactly. So velocity
Derivative of 0 is 0.
Yeah.
Just making sure.
Why would you be making sure?
Yeah. What you passed.
Right.
You really have that. He's like, what did you say? What's a cool trick you can do with this?
So when I
sheet.
went to get it, I got it on command. And people would just like have fun reactions.
Oh, great. The pen doesn't want to work now. Come on.
Don't you have to charge it?
No, it's.
You get batteries.
I know I have it, but it's not a battery. It's connect.
with technology.
Yeah, I know, right?
On paper, it would never happen on paper. You know?
Exactly.
What do you call it when your pen has another name?
Get another pen. You're probably gonna have another pen.
Exactly. Let me see.
But
What?
you're not gonna have another one of those. Like handy,
He is.
Eric,
most likely.
You have your pen with you or no?
Oh, I don't know.
do you need a pen for that? I have one.
You have pen for this? Beautiful. Thank you.
I don't know. Like,
That works.
oh, yeah.
Yeah, thank you though. It just connected. All right. 1, 2t, 3t squared. Velocity, speed is going to be square root of 1 plus 4t squared plus 9t to the 4th. Can't simplify that. And then acceleration is 0, 2, 6t. And then jerk is going to be 0, 0, 6. And that's all of the concepts which we covered. Now I am going to jump to circular motion. And in the circular motion, we are going to use our parametrization for the circle. We have the path, which is the circle, is going to be r of t is equal to r cosine of t and r sine of t. Now, if you are using proper notation, you will see that the lowercase r with the arrow is a vector valued function, which is representing the path, and the lowercase r without arrow is a radius. Now I am going to swap this out for capital R's, so there is no confusion there. We still know it's a radius of the circle. So now, if I know the path, I can quickly come up with velocity. Velocity of t will be negative r sine t, and then positive r cosine t, and then acceleration of t is going to be negative r cosine t and negative r sine t. So now we are going to graph the circle. Okay, fine. No, I practiced drawing a circle for a long time, so that's why it's so good.
This is the saved copy. Just use that.
You guys, you wouldn't know it. All right, so now here's the. Actually, I don't like it. I'm gonna move it. X and the Y. This is where radius R is. On the other side we have negative R. Negative R? Good. So what do I have? The path, right, which is the R. So the blue vector that goes from the origin towards any of the points on the circumference is going to be r of t. This particular one is r of 0. Right? And then you have r of pi over 2. And r of pi. And r of 3 pi over 2. Then you have the velocity one. Well, that better have something to do with our tangents. And it will, because if you observe the vector, you have r sine t, so at 0 you are getting 0 and then r. So we have, let's use actually different color. How about green? So this is the velocity vector at 0. It's going to go that way. And then another velocity vector at pi over 2. And another. And I hope that you can see that these vectors will bend, will turn the circle. V, velocity of 3 pi over 2. And finally, we have the acceleration vector. Acceleration vector is going to point inwards, right, towards the center. So we are going to have these vectors now. And all of these are acceleration vectors. So this is acceleration at pi, acceleration at pi over 2, acceleration at 3 pi over 2, and acceleration at 0. So you have these guys point inwards.
Did you get that from like plugging in these values into
Of the functions, yes, because they produce vectors. You have a vector valued function, and when you have a vector valued function, it has to give you the answer, right, when you plug the values in. Now your parameter could be the angle, could be time, right? They're all interchangeable. Depends on your application, right, of what you're working with. All right, what else do I have? And now we're going to do parabolic motion. Now, all of the formulas you learned in physics will stay the same. We are just going to put them in vectors. So instead of working out separate equations, you just have one single vector to look at. So there it is. Two-dimensional motion in gravitational field. And what you are going to do is you are going to say that your consider an object moving in a plane with horizontal x-axis and a vertical y-axis, subject only to the force of gravity. So we are observing the object, which, let's do this, right, y and x. So the only force is the force of gravity. The initial velocity v0, vector v, at 0, we'll have two components, u0 and v0, so one for x and one for y. And initial position, which is r of 0 is going to be given with x0 and y0. Those are the coordinates in space. So in this case, over here, this point is at x0, y0. That's our initial point for the motion. So what do I have? If all of that is considered, we have that the velocity of t, which is the vector valued function, is given as x prime of t, y prime of t. And that is equal to, we have the u0 and negative gt plus v0. Now, these formulas are actually known from physics. Let me write also the position, r of t. So r of t is x of t, y of t. And we have, since it's a parabolic motion, so we have u0 t plus x0. You are actually integrating this, if you are interested in which way we obtain this. So u of 0, t of 0, u of 0 t plus x0, and the second one is negative 1/2 gt squared plus v0 t plus y0 as the constant. Now, all of the formulas which you see over here are the formulas which you know from your previous education with physics class and so on. You have the notion that when you throw something, the parabolic motion will obviously bring it to the ground. The y velocity changes all the time, where the x velocity is constant. Now, you can observe that when you throw something vertically up. When you throw something vertically up, your hand is giving it the initial velocity of v0, and the gravity will be slowing it down. So, object will eventually stop at the maximum height, and then it will start falling, in which case, when it stops, the initial velocity for the second part of the journey is 0, because the object stopped at the top. So this becomes 0, and then negative gt starts accelerating the object down, giving it more and more velocity as the time passes. Now, sure, there's air resistance and the shape of the object and all these kind of things that could slow it down. It's not the same if you throw the paper or if you throw the marker, but that's because of the air. If you take a feather and a cannonball and toss them in a vacuum without gravitation, or just in a pure gravitational field, they're going to, in a vacuum, they're going to fall. Now, the integral of these two is simply, when you integrate the constant velocity, you'll pick up the t plus the initial position, and then when you integrate this guy, you get your parabolic motion. So now, if you are throwing object, right, this here will capture the location, the height. So this one captures how far it goes in terms of the x-axis, and this one describes the y coordinate. Now, if you have a basic throw, I'm not talking about baseball curveballs and stuff that is, I'm talking about, let's do this experiment now. When I throw the marker, actually, even though we are in a 3D space, the marker will fly in 2D. Does it make sense? So this marker is going to go in 2D, and this is enough for us to describe the motion. I don't need a third-dimensional motion equation for something that is like this.
This isn't definitely 3D this time, but that's the time.
Well, yeah, but I was talking about that.
What would you say?
It's only in the...
So it would be only living in 3D that have like a curve on it.
Yes. So if I'm able to throw something like, let's say, in a helix, right? Like, and in that case, yes, you need.
Because it didn't go left or right when you threw the marker.
So if you were able to like
True.
throw a curveball with a baseball or something, that would
Yes. Yes.
Yeah, you should get a boot.
Wow, when I think about it, yesterday for the first time in my life, I had the opportunity to throw the baseball and I didn't.
What?
Wait, never had a baseball?
No.
Sounds like you're crushed by
You
this.
had a
He
baseball
meant it's been years since you scrolled.
Never in your life have you ever thrown
Never.
a baseball in any situation.
No.
We should go to a baseball game.
How is that even?
I've been at one
Do you not
and
suffer through gym class? Or gym class?
I'm from Europe. We don't have that retarded sport
Where
there.
exactly from Europe are you?
Yeah, my mom's from Europe and she never had field either, so
Exactly.
tragic.
What part of Europe are you
Think
from?
about it.
So,
No.
motion.
Question.
The next, the next concept is to figure out the maximum height of the object. So what's happening with the max height? Well, max height happens when velocity of the object is equal to 0, right? I told you when you throw it when the y component of the velocity is equal to 0. So max height y component of velocity is 0. So that means this negative gt plus v0 is equal to 0. From there, you will get the time, t. And then you will plug that time t into the position to find, in a position vector to find the point, but then the y component gives you the height. So that's how you find the maximum height. So your velocity needs to be equal to 0, because at that point you are at the maximum height. If you're also remembering your Calculus 1 at some point, you learned in Calc 1 that min and max, right, the optimization happens when you set derivative equal to 0. Well, what's velocity? It's a derivative, right? So you set velocity equal to 0, you will find the time at which that situation when the object is at the top and it stops, right? That's why velocity is 0. And then you use the y component of the position function, which is your r of t, to figure out the height. So now use t in y component of position function to find max height. There are other formulas that are, physics specific. We don't really have to push anything further than this, but you can also find the maximum range, which means how far the object would go, and also you can find the time of flight, so how long it takes to reach that. Right. The word problem is you just plug numbers into these formulas. And I think, is that it? That would be very depressing if it is.
You said you wanted to go into that class early, right?
No. That's a lie. What happened? That's that, right?
That one? Oh, that's
Okay, well, that's it for this lecture.